This is Lab 6, Faraday's Law for Physics 2212 by Samantha Hefner. Introduction. The purpose of this study is to study Faraday's Law, which relates time-varying magnetic field to a Curly electric field whose path integral provides an EMF that drives current. And we're going to do this by analyzing the interaction between a magnet falling down inside a tube of aluminum foil. So the main models and fundamental principles we're going to be using today are Faraday's law, of course, and then we're also going to look at Lenz's law, Newton's second and third law, and Biot-Savart law. Quick preview of results. The experimental time we got was 1.494 seconds for the magnet to fall down the tube, and a computational result of 1.344 seconds. So here's just some visual representations of the model. This right here is kind of what's going on inside the tube as the bar magnet falls. And then here is kind of a more analytical approach. This is Lenz's law that is being displayed right now. So you can see the magnet traveling down. It has its own magnetic field, and then also the motion causes another EMF and a magnetic field that will act upon the magnet and, in theory and in actuality, slow down the magnet while it is falling through the tube. Okay, so our experiment. The foil width is 0.5 centimeters. The tube length is 46 centimeters. The inner radius of our tube is 1.25 centimeters. The mass of our bar magnet is 23 grams. Our system that we're going to be looking at is the aluminum tube plus the magnet, and then the surroundings, everything around it. Our initial conditions, we're going to have t is equal to 0 and velocity is equal to 0. Also, in this experiment, we're going to assume that air resistance is negligible. So here are the 5 trials. We dropped the magnet down the tube 5 times and recorded how long it took. So for trial 1, we got 1.5 seconds, trial 2, 1.52 seconds, trial 3, 1.48 seconds, 4, 1.44 seconds, and 5, 1.53 seconds. On average, we got a time of 1.494 seconds. And then here's how we are going to display it computationally. So obviously we have to set up the geometry of the tube. We have our length with that, which I showed before, of 0.46, width 0.005, inner radius 0.125. This is obviously in meters instead of centimeters. And then over here, we have our properties of our magnet. We're also going to have to create a function to calculate the magnetic field of the bar magnet. We did do this in lab 3. So obviously we have our mag, our hat. B is our constant times 3 times dot of mu time and r hat, our r hat minus mu over r mag cubed. All right, and then here we can see visually how we show the magnet falling through. We have our force of gravity, obviously is going to be acting on the magnet. Then also our magnetic field is going to be acting on the magnet, and we're going to visually see what all this looks like when put together here. It's not shown in this picture, but as the magnet falls, this little light starts here and goes down here, and then as that's happening, it's creating a velocity time graph. And as you see, our time was 1.344 seconds. Alright, so what if the resistivity of the conductor were reduced as close as possible to 0, and how would the dynamics of the falling magnet change? If this were to happen, the induced current inside the aluminum would probably be much greater, increasing the internal magnetic field and preventing the magnet from falling. And if holes or slots were cut into the hole, this would affect the ring currents in the model. The induced current inside the tube would likely be less, and the magnet would probably fall much faster. Possible source of error as well in this lab was incorrect time measurements or just general measurement errors. So in conclusion, in this lab we aim to study Faraday's law, specifically the property that a changing magnetic field induces an electromotive force in a conductor. We did this by observing a magnet falling down a tube of aluminum foil. We found that it took the magnet on average 1.494 seconds to fall. Thank you very much.